Alright, so here's a review of lesson number 4. Lesson number 4 is entitled Recursively Defined Sequences. These are sequences that use other terms to be created. So unlike the explicit formulas we learned about in the previous 2 lessons, these formulas are going to be dependent on knowing other terms of the sequence, not just the first term and what the ratio or the difference is. So in the opening exercise, it asks us to just go through and determine if each sequence is arithmetic or geometric, and find the common difference or ratio, and also the first term. So essentially, it's just asking us to understand, do you know what the formulas represent? So looking at something like a sub n is going to be an arithmetic sequence. I know that the common difference is going to be 4. And I know the first term is going to be 6. For b sub n, because we have something with an exponent, I know that that's going to be geometric. I know that the first term is going to be 7, and the common ratio is going to be 2. So let's take a look at another sequence. So we've been writing explicit formulas for sequences. We know explicit formulas help us define other terms of the sequence by just knowing the first term and either the difference or the ratio of the sequence. Recursive sequences are based on rules. So it's all rule-based sequences. So one of the things that we've been doing in the previous lessons is really describing and being specific about our description of each sequence. That's tremendously going to help us with our recursive sequence work. So in example 1, it gives us a sequence of 5, 8, 11, 14, 17. It says describe the sequence by defining the first term and its pattern. So we can say that the sequence starts at 5 and each term is, we notice that there's a common difference here, so it is 3 more than the previous term. So in starting to look at what a recursive sequence is, we can answer these 2 questions. If we know a sub 3, how do we get a sub 4? So a sub 4 is equal to a sub 3 plus 3, because each term is 3 more than the previous term. If I wanted to find a sub 7, I could say a sub 6 plus 3. So now we can represent this sequence as a recursive sequence by using n instead of the numbers 4 or 6 or 7 or 3. So if we know any term is a sub n, we can use that to represent the next term, the previous term, etc. So if I have a sub n, the next term is going to be a sub n plus 1. Because if n was, say, 4, the next term would be 5, so it would be 4 plus 1. So if I want to write a recursive sequence using this idea, I can say any term plus 3 is equal to the next term, a sub 1, n plus 1. Now, normally we don't write a sequence like that, so we'd actually rewrite that as a sub n plus 1 equals a sub 1 n plus 3. So that would be our recursive sequence. Notice the recursive sequence is very different than the explicit sequence, because the recursive sequence is dependent on you knowing one of the terms that's next to the term that you want to find. So I need to know the previous term. So if I wanted to find the 207th term, I would need to know the 206th term if I wanted to use this recursive formula. Let's look at 2. 2 says, consider the recursive sequence. So now this time they're giving us a recursive sequence, and they're asking us to find the pattern. So it says a sub n plus 1 is equal to 3 times a sub n. So what this is telling us is that each term is equal to 3 times the previous term. So each term is equal to 3 times the previous term. So you can start to see why we spent all that time describing sequences in the first few lessons. So if I want to find the first 5 terms, well, the first term they give us, a sub 1 equals 2. If I want to find a sub 2, I'm going to say 3 times the second, the number 2, because that was the previous term. So a sub 2 is going to be 6. If I want to find a sub 3, I'm going to say 3 times the previous term. So that's 18. If I want to find a sub 4, we're going to say 3 times the previous term. So that would wind up being 54. And if I want to find a sub 5, that would be 3 times the previous term. And that would be 162. Now, the interesting thing about recursive sequences is you could also show them as a recursive formula for the same sequence. So now we have multiple things that we can show for each sequence. So now that we know this sequence, it goes from 2 to 6 to 18 to 54 to 162, we could see that this is going to be a geometric sequence. And we have a common ratio of 3, right? The common ratio is found by dividing the second term by the first term, so we get 3. So the explicit formula for any term of the sequence is going to be the first term times 3 to the n minus 1. Now, within recursive sequences, sometimes a notation can be shown differently. So if you notice in this previous example, we showed a term and a term separated by +1. Well, instead of +1, we can also show a term and a term separated by -1. This means the same exact thing. This is still saying each term is equal to the previous term plus 4. So explain the pattern of this sequence, we can say each term is equal to the previous term plus 4. So b sub n minus 1 is representing the term before b sub n. So if I want to use this information to write out the first 5 terms of this sequence, I can say b sub 1 equals 7, b sub 2 is equal to the previous term, 7, plus 4, so that's 11. B sub 3 is equal to the previous term, plus 4, so that's 15. B sub 4 is equal to the previous term, plus 4, so that's 19. And then b sub 5 is equal to the previous term, plus 4, and that's 23. So then if I look at the pattern that's created here, 7, 11, 15, we see it's an arithmetic sequence. And the explicit formula for that arithmetic sequence is going to be b sub n is equal to the first term plus the common difference, which was 4, times n minus 1. So now what we can do is we can represent each one of these sequences using both a explicit and a recursive formula. The next question asks that we can define an arithmetic sequence with a common difference d as, so I can now say any common difference equation is going to be a sub n is equal to a sub 1 plus d times n minus 1. Or we can also show this recursively. So I can say any term is equal to the previous term plus the common difference. We could also define geometric sequences this way. So geometric sequence, we said we'll use b sub n just so it's different. is going to be the first term times the ratio to the n minus 1. Or we could show this recursively and say any term is equal to the previous term times the ratio. So, let's use this information to answer some questions. So it is important to remember that there are two parts to any recursive definition sequence. We need a first term and then we need a rule. So how do we get to the next value? So let's take a look at this first one. So it gives us a sequence of 9, 1, -7, and -15. So we see that they have a common difference here of each time we're subtracting by 8. So if I wanted to give a recursive sequence for this, I know any term is equal to the previous term minus 8. That's my recursive sequence. To find an explicit formula, I would give a sub n is equal to 9 minus 8 times n minus 1. For the next example, we see that this is a geometric sequence. To show this recursively, we would say any term is equal to the previous term times the ratio. So in this case, the ratio is 5. And then the previous term is a sub n. If we wanted to find the explicit formula, this would be a sub n is equal to the first term times the ratio to n minus 1. So there's going to be some reasons why we need the recursive sequences and some examples where we might need the explicit formula. So we want to be able to show both. So we get two more. So for this third one we see again, it's going to be a arithmetic sequence. So I can see that the recursive sequence is going to be any term is equal to the previous term plus 6. The explicit formula is going to be any term is equal to the first term plus the common ratio times n minus 1. For the last one here, we have to find the common ratio. I know it's definitely not arithmetic because there's not a common difference there. So I'm going to take the second term and divide it by the first term, and that gives me 2/3. So now we can say the recursive sequence is any term is equal to 2/3 of the previous term. If I wanted to show this as an explicit formula, we can say it is the original value or the initial value times 2/3 to the n minus 1. Now sometimes recursive sequences are easier to use with like these real life examples, especially because sometimes they have a sub 0, and that's kind of hard to do when we have a regular sequence. So for number 5, it says the amount of medicine initially given to a person is 120 milligrams, and every hour the number of milligrams remaining is 15% less. Write a recursive rule for where a sub 0 represents the initial amount. So if we had a sub 0 is 120, if I subtract 15% from that, so if I find 15% of 120, that's 18, and then 18 minus 120, or 120 minus 18 is 102. So I know after 1 hour there's 102 milligrams left. Then if I do 15% of 102, subtract that from 102, I get 86.7. So we see this is not going to be a common value. Because it's a percentage, it can't be the same every time. So we know that this is going to be geometric. So I need to find the common ratio. So the common ratio is going to be taking the second term and dividing it by the first term. So that'll figure out how much our ratio is. which gives us 0.85. So my common ratio is 0.85. So essentially, if I multiply each term by 0.85, I get the next term. So if I want to find a recursive sequence, I'm going to say any term of this sequence is equal to 0.85 of the previous term. So essentially, if I know how much of this medicine is in my bloodstream after 10 hours, I just multiply that by 0.85 and it'll tell me how much it is in the 11th hour. Now, the other thing that comes up within arithmetic sequences and geometric sequences is there's always that pattern. Well, sometimes sequences don't necessarily have a pattern that has a common difference or a common ratio. Sometimes they can be defined by using both a common difference and a common ratio, which causes us to not really have a specific type of sequence. It's still a sequence, but not necessarily an arithmetic or geometric one. These are usually defined as recursively defined sequences. So example 6 shows us one of these recursively defined sequences. So it tells us a sub 0 equals 4, and it wants us to find some of the rules, and it wants us to find some of the values of these terms. So it says, describe the pattern this rule defines. So what this rule is telling us is we're going to find any term, we're going to multiply the previous term by 2 and add 3 to get the next term. I see that because this shows us this is the previous term. So we're multiplying the previous term times 2 and then adding 3. So if I know a sub 0 equals 4, I can find a sub 1 by saying 2 times 4 plus 3. I'm taking the previous term, multiplying it by 2, and adding 3. So that gives us 11. To find a sub 2, I'm going to take 2 times the previous term plus 3. So that's going to give me 25. To find the third term, I'm going to take 2 times the previous term and add 3. That's going to give me 53. Number 7 says to find the fourth term of the recursively defined sequence. So again, they give us the first term, a sub 1 equals 2. To find a sub 2, we need to know a sub 1. So we're going to take 3 times the previous term plus n. In this case, n is 2. So if I do that, I get 8. To find a sub 3, I'm going to say 3 times the previous term plus n. And that gives me 27. Then I'm going to say a sub 4 is equal to 3 times the previous term plus 4, which gives me 85. And if you look at that pattern 2, 8, 27, 85, it's not geometric. There's no common ratio. It's not arithmetic. There's no common difference. It's just a sequence, right? There is a pattern here, which is why it's a sequence. It's just a recursively defined sequence. Next page is your homework, so please work on that. We'll go through any questions that you have on it tomorrow in class. Hopefully this video helped.